Today we'll be exploring how composites are used in rocket components and nozzle. So composites have been seen with increased interest in the past decades, especially in the rocket industry, due to the many applications of these materials in such areas. So just an overview, composites have enabled the ability to decrease weight of the vehicle, which would allow for increased payload to orbit for the same amount of fuel, and it could help advance aerospace research in the material science front, such that these findings can be shared with other industries. And as an extension from the previous slide, some significance of this project is to analyze how composites fare in comparison to alternative solutions, which would help lead into the discussion of the future prospects of composites in general. The objective of this project is to determine what composites are currently used in modern-day launch vehicles and the reasons they are used. It would also be important to see how these different components are manufactured and fabricated. We will now briefly go over the performance requirements, which are based on the Falcon 9 launch vehicle. So firstly, it will be important to consider the thermal loads to the structure, and this will consist of the fairing temperature during flight, since the fairing is predominantly made up of composites. Also included will be the combustion temperature for the two propellants and the wall temperature for the combustion chamber, since there may be pressure vessels or other internal components made up of composites. Other loads to consider are those due to pressure differential as the space vehicle leaves sea level, because the composite material should also be able to withstand the possible hoop stresses associated with it. Mechanical loads will also play a large role, as these will comprise of the overall thrust force and mass, the acceleration envelope in the lateral and axial direction, and the vibration profile. As a result, the composite will need to be constructed in such a way that it will be able to reduce shock due to vibration, and the material should also be able to withstand these stresses and moments to the system as a structural component. It would also be important to consider the environment, most likely in the Cape Canaveral area where the launch site is. The ambient temperature lies between 56 and 90 degrees Fahrenheit, and the humidity is between 67 and 78%. Because the rocket is reusable, it would ideally provide up to 10 launches, and some of the cost breakdowns are also listed. For each category, the composite structures are highlighted in yellow. And now moving on to the composite materials used for these components. So here's an overview of the composite materials used for the body component of the Falcon 9 launch vehicle and other general rockets in the market. The fairing is made from carbon fiber reinforced polymer, the heat shield ablator will be made from pica, and the landing legs and inner stage will both be made from carbon fiber epoxy laminates overlaid on aluminum honeycomb cores. These cores are designed to be lightweight and are used to increase stiffness and to help with shock absorption, and this is especially important for the inner stage because it is literally sandwiched between the first and second stage. And this will also be important for the landing legs because this will take on the weight of the entire vehicle upon touchdown. In other rockets, pressurized tanks can be fabricated using continuous carbon fiber filaments on top of metal liners to combat hoop stress and help fortify the pressure vessel in the radial direction. Using continuous fibers can also increase the structure strength, the modulus. In the past, carbon composites were not used for tanks because they became brittle under cryo settings, such as being exposed to liquid oxygen, and they were deemed flammable, so this is a re-emerging concept. The nozzle contains a lot of ablatives, so the composites used will be glass or carbon cloth phenolic, which has the ability to absorb heat as it changes state. In heat shield tiles, silica fibers are used because they are great insulators, and the nozzle extensions are usually made from high-temperature carbon-carbon composites due to their good thermal and mechanical properties. Overall, most of these components are structural parts that resist tensile, compressive, and bending stresses or moments, so mainly long-oriented and continuous fibers are used, although continuous fibers can be used for impact and corrosion resistance coating. This would eliminate many discontinuous composite manufacturing possibilities like spray-ups. And for the same reason, fillers are not often used, as to not compromise the integrity of the structure, especially when the goal is to maximize the material strength and modulus. And here are some pros and cons of composites in rockets. They are lightweight, which reduces the fuel required for the same amount of thrust and specific impulse, and therefore increases the thrust to weight ratio. Their high strength and modulus also satisfies the performance requirements demands. And anisotropy is also particularly important because the vehicle's flight trajectory consists of both axial and lateral accelerations, where higher strength in one direction may prove beneficial. And some primary disadvantages are its high cost, resin toxicity, and labor-intensive manufacturing processes. The major alternative to composites are metals, which are widely used today. The most popular metals used are aluminum, which has a good strength to weight ratio and is easy to weld, and stainless steel, which is durable and corrosion resistant. Titanium is also used a lot in engine components since it has a high melting point, which is important for systems like turbines where performance is enhanced with increased temperature, although the material's operating temperature is the limiting factor. And here's a comparison between the density and mechanical properties of composites and metals. It is apparent from the figures that composites have a low thermal expansion coefficient compared to metals, which indicates that there is more dimensional stability and is especially important in parts with small tolerances. Composites also have a high modulus and strength for a lower density, which implies a major weight saving, although for a higher price. Some composites manufacturing, fabrication, and testing methods will be introduced. This is the manufacturing and fabrication process for composite structures with an aluminum honeycomb core like the landing legs and inner stage. A composite layup is initially done, which consists of selecting a woven fabric and resin, and afterwards the prepreg is rolled onto a semi-automatic lay-down machine where the voids are removed. The inner skin will then be transferred onto the bonding mold. In conjunction with the layup, an aluminum block can be machined to a desired thickness and will subsequently be shaped into a honeycomb structure and arranged on the layup. The outer skin will then complete the sandwich structure, and the parts will be cured in an autoclave and tested afterwards. This is the manufacturing process for the nozzle, along with some of its dependencies detailed in the gray boxes. During carbon cloth manufacturing, the weaved cloth will be carbonized at high temperatures and impregnated with heated phenolic resin. 2 tape wrapping operations will ensue. In the first one, tape will be wrapped onto a mandrel at a desired angle, usually between 30 and 60 degrees. The wrapping depends on the heating and cooling inputs, roller pressure, machine speed, and tape tension. After initial cure, the second tape wrapping cycle can be performed. The product will then be post-processed and tested. Here are just a few tests that can be done as validation. Non-destructive testing includes computer-controlled scans, using ultrasonic probes, and testing part remains to verify proper curing and satisfactory mechanical properties. Other quality control measures are burst tests, which are destructive, and fiber matrix strength tests, which are listed. These can be used to test the interfacial and shear bond strengths between laminates. Lastly, we can look into the cost, market viability, and impacts of composites. Many factors impact costs, such as the material used, the product forms, the processing techniques like preforms, autoclave curing, and quality control and testing. For a small economic batch size, the largest cost allotment is in equipment such as autoclaves and layup machines, for example. The second largest is in labor, since composite layups are time-intensive and labor-intensive. Tooling like molds are also pretty sizable in cost, followed by materials, although a trend can be seen with carbon fibers in the past year, where the price per kilogram is decreasing, possibly opening up a future market. So having said that, within aerospace there is a growing market. For example, carbon-carbon composites have seen an expanded use from solely solid rocket motor nozzles to liquid rocket nozzles as well. In the past years, NASA has also been developing composite tanks that are suitable for cryogenic fuel. Other applications of composites that will see a larger market are those associated with consumers, as carbon fiber prices decrease. These industries are with sporting goods, general consumer goods, and transportation vehicles, for example. So here are just some societal and environmental impacts. Societal impacts involve safety, particularly in dealing with toxic resin and the heavy machinery associated with the composites manufacturing process. Environmental impacts include high energy usage, greenhouse gas production, and the fact that composites are not commonly recycled. As more industries continue to adopt these new materials and alleviate these impacts and concerns, the composites market prospects look optimistic. Here are the references used. And that concludes the presentation. Thank you for your attention.